Hello everyone, and welcome back on the third session on electromagnetism. So today we will be discussing about a topic named force on current carrying conductor that is placed in a magnetic field. So there was a scientist named Lorentz. He just wanted to study what happens when a current carrying conductor is placed in a magnetic field. Since a magnet is there, it means magnetic field must be there. And if you see here, this conductor, a wire, is being attached with threads to a battery key, right? That acts as a source of current, right? So he just wanted to see what happens when a current carrying conductor is placed in a magnetic field. So this was the setup that he used. So what he noticed, when no current was flowing, means the circuit was open, there was nothing, no movement was there, he couldn't find anything unique. And the moment he switched on current, he closed the circuit, he made this battery to work. He saw when he switched on, there was a deflection in the wire. That is the current carrying conductor, or I can say that is a material that was making the motion of electrons possible, right? So what he saw, that when the terminals are kept like this, it was giving some other direction, and the moment the terminals were changed, I mean to say, when the direction of flow, the direction of current was changed, there was change in the deflection of the conductor as well. It simply started swinging in the opposite direction. So he tried to relate it to Newton's first law of motion, that is law of inertia. So according to Newton's first law of motion, a body at rest will remain at rest, and a body in motion will continue to move in the same direction with same speed until and unless some external force is applied on it. It means some external kick is required to make a thing work. If a body at rest, you need to apply a force to bring it into motion. And if your body is in motion, you need to apply some force to bring it at rest. So same way here, if this conductor is at rest, it means if it is showing you some motion, it means a force must be acting on it. But he was not at all applying any force here. He was not at all touching this conductor physically. So he thought that there must be some force acting on it. And from where that force is coming, he actually found out that if you place a conductor in the magnetic field, other than the direction of magnetic field, only then the swing of the conductor was there, right? So it means this combination was actually giving the deflection. This combination was creating a force in the system that was making this wire move, right? So he named this force as Lorentz force. So this was the setup. So when he changed the terminals, like suppose it was moving in the forward direction, when the terminals were changed, it started moving in the backward direction, right? And when the circuit was closed, it was open, then it was not showing any deflection. So he found out, he simply experimented, and he came to a conclusion that how the force is going to act. And this was given by Fleming's left hand rule. And according to Fleming's left hand rule, if you have your left hand, right, like this, you need to keep. If you stretch the forefinger, the central finger, and the thumb of your left hand mutually perpendicular to each other. If you see here, these fingers are mutually perpendicular to each other. Can you see here? So I can mark here. It means there is x-axis, y-axis and z-axis, right? We have y-axis here, x-axis and z-axis. Fine. So if they are placed like this, right? Now if suppose, I repeat what is Fleming's left hand rule. Stretch the forefinger, central finger and the thumb of your left hand mutually perpendicular to each other. If the forefinger indicates the direction of magnetic field, the central finger indicates the direction of current, then the thumb will indicate the direction of motion of conductor. That is, in this direction, the wire will start moving, right? In this direction, force is going to act automatically. The conductor will start moving in this direction. So this was Fleming's left-hand rule. Now, if you see here, if you have current in this direction, magnetic field is going to be in this direction, then force will be exerted by thumb. So in this direction, the conductor is going to move. It means if I represent current on x-axis, right? Current is here on x-axis, right? Then y depicts your direction of magnetic field. Then the z-axis represents the force, the direction of force in which it is going to make the conductor move, or the motion of the conductor will be there, right? Because of the force acting. And the force, he named it as Lorentz force, right? So this is your Fleming's left-hand rule. So let's talk about the points that he observed. When no current is flowing, it means no force. Since no current will be there, it means open circuit is there. It means current is not going to flow. Since current will not be flowing, it means there will be no force acting, right? And when current is passed in the direction from A to C, now suppose I mark it as A to C, right? This direction current is flowing. Then a force acts on the wire in the direction perpendicular to both the direction of current and the direction of magnetic field. Due to the force F, the conductor begins to move normal to the plane of paper in outward direction, that is in the Z direction, right? On reversing the direction of the magnetic field or the direction of current, because when you are going to change, the terminus polarity is going to change, or otherwise physically I can change the poles of the magnet. There is going to be reversal in the direction of force. With the result, the motion of the conductor is also going to be in opposite direction. And he now tried to find out on what factors we discussed about Lorentz force. So we have Lorentz force. So on what factors this force depends? He just tried to work on this, and through experimentation he found out that this Lorentz force, it is directly proportional to the length of the conductor. What is the length of the conductor? It will make a difference. It is directly proportional to the strength of the magnetic field. So what is the strength of the magnetic field? That is also going to make a difference, whether the magnet is strong or it is weak in nature, right? And it will also depends upon the strength of the current that is passing through the conductor, whether it is only a cell or a battery, and if it is battery, then how strong it is, how many cells are being connected to it. So all these factors, if we combine, we will be getting F is directly proportional to IBL, right? So he just gave this formula, that is F is equal to remove this proportionality sign, he introduced a constant whose value depends upon the choice of the units, right? So in the SI units, the unit of B is such that K is equal to 1. He introduced a constant K. It is IBL, right? So this was the experimental setup, and this was the formula that what is the magnitude of force, what are the factors on which this force depends, right? And I again repeat the Fleming's left-hand rule for the direction of force, and it was, this is how we calculate, that if we stretch the forefinger, the central finger and the thumb of our left hand mutually perpendicular, these are mutually perpendicular to each other. If you see here, just like this, mutually perpendicular to each other, then the forefinger indicates the direction of the magnetic field, the central finger indicates the direction of current, then the thumb gives you the direction of the motion of the conductor, or I can say, because the force is acting in this direction, that's why motion of the conductor is in this direction, and which is given by your thumb, right? So I hope so you remember. So now let's work on the units of the magnetic field, right? And what is magnetic field? This is the force acting on the current carrying conductor, but we want to find out the magnetic field. What are the units? So let's talk about that. We saw that F is equal to IBN, right? So I want to find out the units of B. It means B will become F upon IL, right? And the SI unit of force is Newton. The SI unit of current is ampere. And the SI unit of length is meter. It implies the SI units of magnetic field are Newton per ampere per meter, right? Or the other units we call this as, this is also named as Tesla. This is named as Tesla, right? And the symbol is capital T. This is also, we also name it as Weber per square meter. So these are the three different units. In exam, they may ask you that write the units of magnetic field in SI, or it may be represents the units of magnetic field in terms of force. Force means they are actually talking about the unit that will be including Newton, right? That will include Newton. And the other is Tesla, and they may give you MCQ that this unit represents what, which physical quantity is being represented by Weber per square meter. So we need to know. Now the next topic is regarding application of your Fleming's left hand rule. So we have your simple DC motor. We have simple DC motor. So first of all, we need to understand, if I'm saying DC, what does it mean? DC. DC means direct current. And if I say motor, I mean to say electric motor. What is an electric motor? An electric motor is a device which converts the electrical energy into mechanical energy. So electrical energy, it gets converted to mechanical energy with the usage of DC, right? So this is your DC motor. Let's talk about the principle of DC motor. A DC motor works on the principle that when an electric current is passed through a current conductor placed normally in a magnetic field, a force acts on the conductor, as a result of which the conductor begins to move. Thus, the mechanical energy, or you can say the work, is obtained, and the direction of the force on the conductor is obtained with the help of Fleming's left hand rule that we have just discussed. Okay. So now let's talk about the important parts. Let's talk about the construction. So these represents the two strong magnets. Suppose this is north and south poles of the magnet. So you may ask how this is going to happen. You consider here a huge magnet, and on this side also consider a huge magnet, right? And you think this is the north pole of the magnet, and here it's going to be south. This is going to be south. Here this is the south end of the magnet, and here it's going to be north, right? So this is north and south. The opposite polarities are to be kept, right? And in between, an armature coil is there. This is your armature coil, right? Armature coil. And to increase the effect, we use soft iron core. Soft iron core, and we have discussed this many a times. Why soft iron core is used? Core, sorry, I have written here coil. Soft iron core, right? And next is your carbon brushes. We label them as B1 and B2. These are two carbon brushes. This we know that key is there, then battery is there, and then we have a rheostat. This is your rheostat, so that we can change the resistance, right? And the next is, if you see here, these are horseshoe magnet, fine. And now this what is this? This is an axle. So what is this axle? When we will be converting electrical energy into mechanical energy, we attach the parts with the axle. It all depends on what sort of work we want. Suppose it's a washing machine, you want to spin the clothes. Suppose it's a mixer grinder, you want to grind something. right? Suppose it's a motor of a fan. So you stick or you fix up wings there, right? So this axle is an external part, and this is all the internal part which is not visible to us. This is something inside we call electric motor, and this is actually visible to us just beyond the axle, whatever parts we attach depending upon what is our requirement, right? So these are the important parts. Now let's see what I think I have told you, what North and South Pole, what they're going to work. They are going to provide a magnetic field, right? And these are brushes, carbon brushes. These, and if you see here, these are also known as split brushes, or you can say split parts are there offering. If you see here, it actually makes a whole ring, but this is being cut from the center, right? But these are the two parts of the same ring, fine? So these are also known as the split ring commutator. I'm using the word commutator. Let me write the whole. It's a split ring which acts as a commutator. Commutator. So what is a commutator? Commutator basically reverse the direction. It commutes. Commutator word has been derived from commute, and commute, it's going to reverse the direction of current. Reverse the direction of current, right? So this is the main function of your split ring, right? Or I can just if you want, I can speak out again about the function of split rings. The split rings, these split rings, right, they act as commutator. With the split rings, the direction of current through the coil is reversed after each half rotation of the coil, and thus the direction of couple rotating the coil, it remains unchanged, and the coil continues to rotate in the same direction. See actually how it happens. It is right now this way. These are the two ends of the spring, right? So when current is going to pass through it, right, when current will be passing, it's going to move. It's going to move. So these two brushes, they are going, no longer they will be in contact with these wires, right? They will move this way. But at this point, they will gain so much of momentum that they will be able to cover the next portion. But if you see here, it was like this, my fingers, the tips are in upward direction. But when they are going to move, it will be in opposite, this way. See here, this hand, it's going to be this way. So they are going to reverse the direction of current. But since they will be in contact with this way, they will keep the current in continuity, and this will keep on moving, right? Since working is not in syllabus, so we will not be discussing about the working of DC motor. But this much you must remember, in exam they ask you to draw the diagram. Sometimes they give you diagram and they ask you to label it, and they ask you to tell any two important parts and write the functioning of those two important parts. So this is how we draw the diagram, and you can talk about brushes, you can talk about this armature coil, you can talk about soft iron core, right? And yes, these parts, battery, no doubt. So this represents your DC motor. So I hope so this part is clear to you, and hope so this video is going to make you understand better about Fleming's left hand rule and construction, and the construction parts, and just I can say the diagram of the DC motor must be clear to you. So with the hope that you are regular in working and you're making maximum use of your time. So I wish and I hope you will be there next time to see my next video. And now after this is your Fleming's right hand rule. We'll be talking about electromagnetic induction, right? So be clear about your concept so that you don't pile up with the things and you mix up the two things, right? So be clear about whatever videos you have already seen, work on it and get prepared with the next video, right? So hope to see you soon. Bye-bye. Take care. Stay safe and stay healthy. God bless you.